Ladies and gentlemen, I'm Wenhan from Shanghai Jiaotong University. Today I'd like to present our paper, Attribute Network Embedding Method based on Joint Clustering of Representation and Network. My presentation will be divided into the following four parts. The first part is background. Network embedding aims to represent the nodes in the network as low-dimensional, real, and dense vectors, which restore the original relationship between nodes in a more efficient way. The node representation can be applied to many common applications, such as visualization, node classification, link prediction, or community detection. Compared to normal network, attribute network contains not only structure information, but also rich attribute information, which is important to network analysis. Most of the existing network representation learning methods expect to preserve the structure and attribute features in the representation space. In addition to the macrocosmic structure and attribute features, clustering, as the most important mesoscopic structure of network, is significant for many network analysis tasks. For example, in social networks, users need to be divided into meaningful social groups to implement functions like user search and targeted advertising. Most of the existing methods ignore the clustering property of network and do not preserve it explicitly in the representation space. These methods learn representation independently and then apply traditional clustering algorithms to the representation, which is not conducive to many downstream applications. In recent years, some algorithms preserve the clustering property in network embedding. For example, network embedding for node clustering, ANEJC model, jointly optimized clustering loss and embedding loss to learn node embedding that preserves network clustering structure. Although extensive experiments have confirmed the effectiveness of NEC, we believe that some important factors have been ignored. NEC adopts non-variational autoencoder and does not reconstruct the attribute matrix, which makes it sensitive to structure noise and attribute noise of network. Moreover, it only clusters the network structure by modularity maximization and does not cluster the representation jointly, which may degenerate the performance of ANEC. To solve these problems, we proposed ANEJC, attribute network embedding based on joint clustering of representation and network. First, it learns the low-dimensional representation of nodes and community distribution in attribute network at the same time. Second, it preserves network structure and node attributes at the same time. Third, it uses Gaussian mixture model and modularity maximization to cluster representation and network structure at the same time. The next part is model description. Here is a table of symbols which explains their meanings in the following parts. Then, here's the architecture of ANEJC, which is mainly divided into the following three parts: variational graph autoencoder, joint clustering of representation and network, and self-clustering. Variational graph autoencoder consists encoder, structure decoder, and attribute decoder. First, the adjacency matrix A and the attribute matrix X are input into the decoder, and n-normal distributions are generated through two-layer GCNs, from which the low-dimensional embedding Z is derived by sampling. Then, the structure decoder reconstructs the adjacency matrix from Z are inner products to preserve the network structure, and the attribute decoder reconstructs the attribute matrix from Z by superposition of multiple fully connected layers to preserve the node attributes. In the joint clustering part, GMM is used to cluster embedding Z, and modularity maximization is used to cluster network structure. In the self-clustering part, the divergence of the soft assignment distribution Q and an auxiliary distribution P are iteratively minimized. Then I introduce them separately. First, based on VAE framework, the variational graph autoencoder (VGAE) is divided into two parts, encoder and decoder. The encoder generates low-dimensional embedding with input adjacency matrix and an attribute matrix. The decoder reconstructs adjacency matrix and attribute matrix with generated low-dimensional embedding. Compared with GAE, VGAE generates a series of normal distribution and samples from it to get node embedding. This method solves the problem that GAE is sensitive to structure noise and effectively prevents the problem of overfitting, so as to have better clustering performance in some situations. Next, I introduced encoder, struct decoder, and attribute decoder in detail. The first part is encoder, which aims to generate the embedding from adjacency matrix and attribute matrix. In ANEJC, we use two-layer GCNs. First, we generate mu and sigma through GCNs. Then we can get n normal distributions by mu and sigma. At last, we use a reparametrization trick to sample the embedding from them. The loss function of encoder is defined as the KL divergence between representation distribution and Gaussian distribution. The second part is the structure decoder, which aims to reconstruct the adjacency matrix from the embedding. In ANEJC, we use inner products, just as what graph autoencoder did. The loss function is defined as the cross entropy between the original adjacency matrix and the reconstructed adjacency matrix. In order to preserve the attribute information at the same time, we add an attribute decoder to reconstruct the attribute matrix. We use three fully connected layers to expand the dimension of embedding layer by layer, and finally get the reconstructed attribute matrix. And the loss function of attribute decoder is defined as the cross entropy between the original attribute matrix and the reconstructed attribute matrix. The fourth part is the joint clustering of representation and network. Here is the introduction and definition of modularity, which is a common method to measure the partition quality of network communities. Higher modularity means better quality of network partition, so we can optimize the community assignment of nodes by maximizing the modularity. In order to calculate the modularity, we need to get the community assignment matrix H. In the original definition of modularity, Hij equals 1 when node Vi belongs to the community Cj, and equals 0 otherwise. One node can only belong to one community. However, many existing studies show that communities in most of the complex networks are overlapping, which means one node can belong to multiple communities at the same time. Therefore, we used the relaxed modularity and replaced hard community assignments H with soft community distribution. In order to associate community distribution with node representation and then optimize the node representation according to the clustering objective, we use a fully connected layer and softmax function to map the node representation to the community distribution. In addition to the clustering of network structure, the output representation of the variational autoencoder can also be clustered, because it contains structure and attribute properties of network. Moreover, the representation of network integrates and compresses the structure and attribute information of network and removes the redundancy. Thus, the clustering of representation is an important supplement to the clustering of network structure. We use GMM to cluster the representations. The lower bound of the log likelihood function of GMM is as follows. In order to realize the joint optimization with the above network clustering, we replace the posterior distribution based on Bayesian rules with the node community distribution represented by fully connected layer, ignoring the items that are not related to the parameters in phi, and marginalizing y. The lower bound can be simplified as follows. Then we use EM algorithm to optimize the lower bound above. The updating rules are as follows. In order to integrate GMM into the neural network, we follow the technique proposed in reference 5 to add the following energy term based on the parameters above. Finally, in order to jointly optimize the clustering of representation and network, the loss function of this part is defined as follows. As we can see, the first term is the negative value of modularity, and the second term is the log sum of the energy terms. Next part, we introduce self-clustering method from DEC model to improve the clustering performance of ANEJC. It uses student's t-distribution metric to calculate the node's soft assignment distribution Q, which represents the probability that each node belongs to each community. And then we communicate auxiliary distribution P, which is used to measure the objective probability that each node belongs to each community. The loss function of this part is defined as the KL divergence between P and Q. Okay, in order to joint optimize tasks of dimension reduction and clustering, we set a unified objective function for every loss function mentioned above. We use Adam algorithm to train ANEJC. For each node in H, we derive the label that has highest probability as the node label Y, which can be used to evaluate the clustering performance lately. Next part, in order to evaluate the clustering performance in ANEJC, we did extensive experiments on both synthetic datasets and real-world datasets. First, we use LFR benchmark tools to generate 4 synthetic datasets. We generate node attributes by the community labels of nodes and add noise to them. Also, in order to ensure the usability and practicability of ANEJC in the real world, we also adopt 3 common used real network datasets, HVR, Cora, and Sightseer. The network parameters are shown in the table. We compared ANEJC with 6 state-of-art network embedding methods, including NEC. For algorithms without clustering optimization, we use k-means algorithm to cluster the generated embedding. For NEC and ANEJC, we directly use the node community label Y as the clustering result. and evaluated them by NMI, normalized mutual information, ACC, accuracy, and MOD, modularity. On synthetic datasets, as we can see, the NMI and ACC of ANEJC on the four synthetic datasets are better than the existing highest values, except that the modularity of ANEJC on one dataset is slightly lower than that of COM-E. It is also better than the highest value in other datasets. Notably, all results are improved compared with NEC. On real-world datasets, as we can see, ANEJC gets at most 21.4% improvement in NMI, 9.1% improvement in ACC, and 4.3% improvement in MOD. Thus, the experiment results on these three real-world datasets show that ANEJC is more effective than other state-of-art network embedding algorithms in clustering. In order to show the clustering performance more intuitively, we adopt the TSNE visualization to display the clustering results of NEC and ANEJC on Cora datasets in two-dimensional space. As we can see, compared with NEC, ANEJC has the better separation effect of yellow, blue, and dark blue nodes, and the nodes in each cluster are more concentrated in ANEJC. The visualization results clearly indicate that the representation generated by ANEJC contains more community information, so the clustering performance of ANEJC is better than NEC. In order to evaluate the influence of each parameter of ANEJC, we give parameter alpha, beta, and gamma different values to analyze parameter sensitivity. We change one parameter each time and fix the other two parameters. As we can see, in the large value range of alpha and beta, the clustering performance is relatively stable. Thus, we can choose their values in the relatively large range. While for gamma, the performance gets better when it increases to 0.05, and after that, the performance gets worse. The best value of gamma on both datasets is 0.05. The last part is conclusion. In this paper, we proposed an attribute network embedding method based on joint clustering of representation and network. It reconstructs adjacency matrix and attribute matrix to preserve network structure and node attributes in the representation space. It clusters representation based on the Gaussian mixture model and clusters network structure based on the modularity maximization. We jointly optimize reconstruction loss and clustering loss to learn the low-dimensional embedding and node community distribution. Extensive experiments show that ANEJC has a superior clustering performance over the state-of-art methods. Also, due to the limit of GCN and modularity calculation, the whole graph needs to be loaded into the memory in each training epoch. Therefore, how to carry out a bench training to improve memory efficiency is our future research direction. Okay, that's all. Thank you for listening.